variety of totally different presentations. I would like to say that a honorary member of scientific committee is Professor John Abel from Cornell, Civil Engineering and Environmental Engineering. He was past president of IASS. And close to the Book of Abstracts, we offer some post-conference proceedings. We have two special issues, one in Applied Sciences Journal published by MDPE in Switzerland, and also Polish Academy Sciences Journal. These are very highly recognized in our country. Some basic facts about our conference are collected in this slide. We have 4 general lectures from Japan, Italy, South Africa, and the United States of America. We have 3 invited lectures. These are domestic lectures from Lublin University of Technology, Poznań University of Technology, and Institute of Fundamental Technological Research, Polish Academy of Sciences, as well as 31 lectures, regular lectures and presentations delivered by participants of this conference. This led to 2 days of our meeting, unusually, and you have some, let's say, listing of how many presentations are from specific centers in Poland. Scientific committee of this conference consisted of 43 members from Austria, Italy, France, England, Scotland, USA, Japan, so highly recognized scientific researchers all over the world. We have no parallel sessions. That is very important. Each participant of this conference will see everything if it is necessary and interesting, of course. We would have some dinners, gala dinner and farewell dinner today and tomorrow later on, 5 p.m. And you are, of course, invited to see our city, as our dean said before. The main organizers and main face of this conference is Professor Jacek Szafran. He is the chairman of organizing committee, and I would like to announce that he was recently elected as chairman of technical committee of ICO in Poland. This ICO committee is relevant to Eurocode number 0, so to the reliability of structures. That is very nice for me because past chairman asked for someone from Łódź University of Technology, and it was very pleasant for me to say that Professor Jacek Szafran is a very good candidate. So we have also some letters supporting us from president of our city, Hanna Stanowska. Maybe you don't know that he graduated from our university, specifically from our department, so that is very pleasant support. And as you most probably noticed from the Book of Abstracts, there is some obituary for Professor Obremski also, who passed away last year. Thinking about this obituary, I would like to say that I was trying to find out his research in Google Scholar or ResearchGate, and first of the articles I found was application of computers for solution of some hexagonal beam structures, bar structures. So this was mainly finite difference approach, maybe not very popular right now. Except of these words I wrote specifically for him in Book of Abstracts that you can read in this book, I would like to say that he personally helped me a lot in my career. Thanks to all these conferences, I was able, as a young researcher, to publish a lot with reasonable review and reasonable time of publications. So I encourage a lot of young people to attend this conference specifically for the same purpose. So pleasant discussion and relatively fast publication. It is not convenient maybe, but I would like to say that we have relatively a long history of our meetings. As you see, the first meeting was in Warsaw 1995. After this conference, Professor Obremski asked the 3 persons to enter his room, and we established some year-to-year meetings to present what we do. So as you see, mainly in Warsaw, Warsaw University of Technology, but some other cities also, Kraków, Rzeszów, Bydgoszcz, Olsztyn, and also Łódź. In 2005, it was very nice for me to get the medal sponsored and designed by Professor Obremski for the first 10 years of presence of IAS in Poland. He broke the conference, I was late. Marcin, that medal is for you and for 2-3 other researchers because you are very devoted to this conference, so I would like to give you some special gift. This is the first book from 1995, collecting the abstracts and larger articles even. From the very beginning, this conference was very international. Professor Obremski was able to invite both people from Russia, Ukraine, as well as United States, Japan, and Western European countries. It was, and still is, very scarce, let's say. That is, as you see, volume number 2. The conference, very large IAS conference in Warsaw in 2002 in Forum Hotel, a lot of guests specifically from Japan. For those who are interested in mechanics, there were even some papers related to application of homogenization method in lightweight structures. So let's say very distant and very theoretical papers at the same conference. Our let's say friendship, I mean the friendship of Łódź with IAS conferences, hosting of IAS conferences, starting in 2011. And we had a very nice dinner at Manufaktura. For those who are out of the city, it is a very recommended place in Łódź, post-industrial, as our dean said, very important for our city. And conference materials brought by Professor Obremski in 2 bags, using the train from Warsaw to Łódź. Not maybe very professional, but very nice. Last conference in Łódź in 2018, we thought with Professor Szafran that maybe it would be the last conference of IACS in Poland. However, our energetic approach led us to what we have right now. And just a few places. We are located in here, Information Technology Center. That is our room. Entrance to the Łódź University of Technology, Aleja Politechniki, as you see, as well as our beautiful and big, enormously big sports bay, where we would have the dinners, and maybe you would like to visit for sport reason. That is Piotrkowska Street. Everybody wants to see that. A lot of people, even out of our country, ask what's going on Piotrkowska Street. So that is very famous Piotrkowska Street. And just the few places, important places for everyone. Maybe you know that Piotrkowska Street looks like that. So Piotrkowska Street is very close to our cathedral. We are located in here, so just the few blocks, as the people say in America. That is a memorial place of priest Ignacy Skorupko, who was very important for our history in 1920. He led Polish troops against Russians during the Battle of Warsaw, as well as the person who is also very important for our city, St. Faustina. She has a specific path in Łódź, and our cathedral is one of them. So please enjoy our city and find everything what is interesting into it. I recognize this conference as open. Thank you very much for being here. We will start the first lecture very soon. Thank you very much. As the chairman of the first session, I would like to say that the first lecture will be delivered in the video mode. This is a lecture of Kenichi Kawaguchi, The title of this lecture is Lightweight Steel Frames Manual Prestress. That is very nice for our department because we are dealing with steel structures. Dr. Kenichi Kawaguchi is a professor in the Institute of Industrial Science, the University of Tokyo. He graduated from Waseda University in 1985 and finished his master and PhD degree at the University of Tokyo. He started his academic career in the study on theoretical and numerical of kinematically indeterminate structures. He also handles structural design and practical developments of structural devices such as tension truss system, maybe systems, world first typical tensegrity structure, new faculty building for engineering department in the university, new types of seismic base isolation systems. That is very interesting for us because we don't know a lot in this area. All of them have been really constructed. He has kept warning danger of accidental fall of ceilings in large public spaces since Kobe earthquake in 1995 and promoting lighter ceiling material, which has been quickly getting popularity in Japan. He is currently serving as one of the vice presidents of IACS and the board member of SEWC, most probably dealing with structural reliability against the earthquake. So I would like to ask our technical staff to start this lecture right now.
Hello? Can you hear me? Okay. So thank you very much for your kind introduction. And thank you very much for inviting me to this LSCE conference. I appreciate this kind invitation from the organizers, and especially from the Professor Safran for his very kind invitation to me. And before, my name is Kawaguchi Kenichi. I'm the professor in the University of Tokyo, and I'm currently a vice president of ISS. And before I start my lecture today, I would like to mention about the very sad demise of Professor Obremski. I would like to share the screen now. 네, 알까나? 사운드入れなかった。サウンド入れるんです。画面があったんですけど。Alright, sorry. ここ上の方していただくと。出てこない。Okay, sorry. No, I say the demise of Professor Obremski has been already mentioned by the organizers in the opening. Actually, Professor Obremski was also my long friend. Actually, my senior long friend, old friend. I met him a long time ago, I think something 25 years ago. And at that time, he has already been one of the popular faces in the annual symposium of IASS. That was in late 90s. So I should say that was in 20th century. At that time, he was very active and he participated in many of our ISS symposia. And then, so I think in 2000, somewhere in the late 90s, he decided to host the ISS symposium, one of the symposium at the Warsaw. So this is a picture of the closing banquet during Nagoya Symposium in ISS, during ISS 2001. And you can see him here. You see my pointer? So he is in the middle of the photo, and actually in the closing session he declared that he would support the host, this annual symposium in Warsaw in 2002. And sorry for this low resolution of the photo, but this is a photograph taken during the opening session in Warsaw Symposium in 2002. So you can see the Professor Obremski here, and also Professor Medwadowski here. So he was very active, especially as a person from Poland. And I think he is not that, so he was rather quiet person, and he probably because he did not speak fluent English, but he has spoken when it is necessary. It was necessary, mainly for the Polish chapter of ISS. So I'm sure that he had felt, or he felt a very strong responsibility as a representative of Poland. And he has excellent leadership, as I believe that in the Poland, as especially in the Society of Spatial Structure Engineering. And this picture was taken when Professor Obremski received lifetime honorary membership from SUK. So even after he joined the advisory board of ISS, he also participated in most of our ISS annual symposia, and also active in other activities. I think that was 2 years ago, and I think I also met him in 2019 in Barcelona. So for me, his demise was so sudden, and I felt very, very sad about his demise. So in my deepest sympathy, I pray that his soul may rest in peace. Okay, so let me start my lecture today. That is about lightweight steel frames, manually prestressed. Okay, so the first thing that I would like to say is lightweight structures requires less material. So recently everybody says about low carbon society, and this lightness and requirement for less material is a promising feature in the low carbon society. So lightweight structures have futures. And it is also desirable to minimize carbon emission and energy waste during their construction. So this lecture is to share my experiences through my very, very small 3 challenges about tension truss dome, tensegrity frames white line 1, and tensegrity frames white line 2. Okay, so when we think about prestress, introducing prestress, say it is very useful to reinforce the stiffness of frame structures. For example, if you have such a braced structure, If you don't introduce any pre-stress, so then if the horizontal load acts to this structure, the brace member in the compression side easily slacks. However, if you introduce pre-stress in tension in the braces, this thin brace member takes compression, so it doesn't buckles until it slacks. So in this way, you can make the stiffness of the frame. Okay, so in this way, so you can utilize the pre-stress to have more effective frame structures, especially in the elastic range. Okay, so when we think about the effect of the pre-stress to the frame structures, there are two aspects. So if you introduce pre-stress to such small structure, okay, so if you don't put any pre-stress, so there are no stiffness. If the external force acts perpendicular to the structure. But if you introduce a pre-stress, okay, you may have a certain stiffness even when the structure is straight. Okay, that is so-called geometric stiffness. However, when you apply the load parallel to the members, so you can double the stiffness again. Okay, so if you don't have any pre-stress, so you just have a stiffness for this side, and this compression side member slacks. However, if you introduce pre-stress, you can use the stiffness of the members in both sides. Okay, so that means that the origin of the structure becomes here at this point. Okay, so you can enjoy the stiffness in both sides. Okay, so you will have the double stiffness of the structure until the pre-stress slacks. Okay, so this means that tension member in the pre-stress can take compression. So this is very convenient and very effective feature of the pre-stress structure. And generally, geometric stiffness, when you compare the geometric stiffness and the elastic stiffness, geometric stiffness is much lower and elastic stiffness is much higher. So say when I use the pre-stress, I'm trying to use this side of effect of pre-stress. Okay, and if we prepare the pre-stress frame, we need to input some strain energy to the structure during the construction. So one of the topics today is how we introduce the energy, strain energy for the pre-stress during the construction. The first challenge was for the construction of tension truss dome. When I was a PhD student, I was asked to propose an extremely lightweight structure for the construction of annex space on the existing building. Because the existing building, this building was not prepared, not designed, because this is old, not designed to have extra building on top of it. So because of that, we need to design an extremely lightweight structure for the annex space of this roof space. And for during that consideration, I thought that why we do not use this say effective feature of lightweight structure. So I investigated to propose some prestressed frame structure. And finally, what I have proposed for this project was this type of unit structure that I say later I named this structure as a tension truss. And this is a unit structure which consists of 4 var link, 1 isolated post, and 8 tension rods. So in this formation, this unit structure has 1 statically indeterminacy. That means the pre-stress mode, it has only 1 pre-stress mode. So all the pre-stress in the members are proportional to 1 mode. And I also plan to introduce how to introduce the pre-stress into the members is to use a small turnbuckle. This is a specially designed turnbuckle, which will be rotated at certain level of torsion to shorten the length of the member to introduce a pre-stress to the structure. And again, see, so that means we need to introduce some strain energy during the construction. And before the construction, we made a mock-up model with 4 units, and we found that, say, experimentally, we evaluated that the torsion with 4 kilonewton centimeter can introduce 10 kilonewton for the actual, to the actual, the longest 10 kilonewton axial force to the longest member of the unit. Okay, so we used this result, and at the construction site, we also used a very special device which is called torque wrench, which clicks at certain level of the torque, fixed level of the torque, and torque, and it becomes it clacks at a certain fixed range of torsion, and it becomes flexible, relaxed when it reached the torsion. So this device was very easy to introduce, very convenient to introduce the torsion and also the actual compression of tension into the member. And this is a result, some measured result at the site. The level of the tension introduced was mostly okay for the design value, but at the same time we have several differences. So I thought that we need to develop some theory later. Okay, so this is a interview after the construction of this tension truss dome. That was construction went very successfully, and I was very happy to realize design such a lightweight structure for the annex of the building. Okay, so this is an interior view of the completed structure, and this is exterior view. Okay, so but during this construction and design, I felt that we need to develop some theoretical theory for the operation of a frame structure with many turnbuckles. Okay, so we have already developed the theory. How to control the length of the members of the frame with many turnbuckles. Okay, but today I don't want to go to the detail. But at the same time, with this formulation, we could calculate the strain energy induced to the structure during the operation. The second example challenge that I would like to share with you is about the design and construction of tensor frames that is called the White Line 1, constructed in 2001. This is a typical tensor frame. This type of structure can stand for its weight and it looks stable. However, the rigidity or stiffness of the of this frame is well known that it is from the geometric stiffness. That means the stiffness of this structure is very, very low, like this, non-linear and very low. Okay, so I propose to add 3 more tendons to this structure. And these 3 tendons very effectively acts as a member to introduce more prestress to this structure. And also it can take the compression after the prestressing. So with this arrangement of members, this, as you can see here, the stiffness of the this tensor frame improves drastically. Okay, so this is the elastic stiffness of this frame. Okay, the original was like this. Okay, so these 3 additional tendons carries the compression, and they behave as a very thin but very stable compression member until they slacks. Okay, so after the slackening, the behavior becomes like nonlinear and low with low stiffness. But say if we design the structure in this elastic range, this structure is stiff, rigid enough to support the membrane roof. Okay, and we made a mock-up model and check the how we introduce the prestress into the structure. And this is a view of this frame during the construction. So as you can see here, first we put the main tendon for the original tensegrity, and we added 3 more tendons. Okay, so to take the compression load or stress under the loading, external load. And we put the strain gauges, mounted the strain gauges of all the members, and we monitored all the tensions at the construction site. And again here, we also used the human power to introduce the tension into the frame, prestress to the frame. Actually, there is a limit of the amount of the tension that manpower can introduce by the turning turnbuckle of the tension member. Actually, I will show you later, but that is normally about 40 kilonewton. So at the construction site. Okay, so we limit, in this case, we limit the maximum tension that the manpower, one person can introduce to the one tension member is to the 30 kilonewton in this case. So in this diagram shows step, construction step, and also member force versus member force. Okay, so this member was used as a control member for the prestress introduction. So this operated rod reached 30 kilonewton when the structure was completed. But during that operation, other tension members reached the higher level of tension. So, for example, the highest one was 200 kilonewton. Okay, through this procedure, it is possible, okay, to realize the much higher prestress level of members in the structure. Okay, so this is a view of the skeleton prepared for the membrane roof, and this is a interior view of the structure when it was completed. So as far as we understood that that was the world first structure using the typical tensegrity skeleton as a structure member to support the membrane roof. Okay, so for the introduction of pre-stress to this type of steel frames, the turnbuckle is very important. Okay, and so we tested and checked the behavior of the turnbuckle. Again, I do not go into the detail of this experiment, but we measured that the maximum tension that one man can introduce to the one rod through by turning the turnbuckle. In the laboratory, the amount was something like 80 kilonewton. Okay. However, the condition of working is very much different in the construction site. So we limit the maximum of the tension that one man can introduce to the one tension rod to the 40 kilonewton, okay, or something about 40 kilonewton. So, for example, the man is standing on such unstable decks. So we need to expect the much less level of the tension that he can introduce to this the tension members. Okay, the third example that I would like to share is a tensegrity frames wide line 2, which was completed 2017. Okay, so in this case, we designed two types of tensegrity frames to support the membrane roof. Today I just explained about this tower type tensegrity. Actually, we designed this pentagonal type, but today I don't speak about this because of the time. This is a arrangement of the member of the tower type tensegrity. Okay, so as you can see here, this is more complicated than the former one, and we have many tension members and compression members, and also many turnbuckles installed to the most of the tension rods. Okay, so this time it was. So we don't have enough time for making a full-scale mock-up. So instead of that, we made a 1 to 10 scale model to check the pre-stress introducing scheme. So first, we prepared these two tensegrity frames, and we attached these two models each other to make a tower type structure. Okay, so this is a connection area, and also during the construction, we see the frame deforms actually in a very large scale. So some of the detail must be designed to accommodate such a large deformation. Right. So for the construction of this type of tower skeleton, okay, first we had this triangular tension members at the bottom of these two units, and after combining these two units, we add another tension rods, and then finally we removed these triangles, okay, so that we can say have a more simple tensor. We can enjoy the appearance of more simple appearance of the tensor tower. And as you can easily imagine, it was very complicated to establish or construct this type of tensor frames, especially the balance of the tension in the frame. Okay, so again here we limited the level of the tension of the controlling member to the actually 40 kilonewton. Okay, so first, for example, in this case, first we operated these three members, and until they became 30 kilonewton. Okay, then we added another three members for the controlling. Okay, and these members was operated until they reached 35 kilonewton. And during this operation, for example, in this case, this former controlled member reached, say, the higher tension. Okay. So in such a way, we gradually change the controlling members until we could introduce the necessary tension to all the members of the tensor tower. Okay, so can you see? So this is how we operate tension rods. This way is a little bit convenient because here I'm using a machine. So because it is very easy to control them by ask them to rotate the thermocouple. And this is another a video from the construction site. So first we assembled the unit of tension of tensority, and then we put this tensority to another tensority that was waiting here, somewhere here. Okay, so this is how we constructed the tensority skeleton. Okay, so this is some photos of details of the structure, and this is the interview completed. Okay, so this is another result of the measurement during the construction. So the final controlled member, tension member, this is a step versus the level of actual force. And you can see that the level of the tension member, say, finally gradually converged to the 40 kilonewton, because this member was used for the final controlling member to introduce a prestress to the tensor tower. Okay, and this is the extra view of the completed structure. Okay, so now I would like to make some remarks from my talk. Okay, the first, lightweight structures require less material. This is a promising feature in the low carbon society. For effective use of this feature, it is desirable to minimize carbon emission and energy waste during construction. The pre-stressing is a good way to make a lighter structure, and one of the most effective and energy saving scheme for its construction is direct use of human power. So that I wanted to show through my challenge. And although limit of human power is low, you can find a way for making the best use of human power. For example, in my case, the level of tension was limited, but say we try to make it the best use of this power or to making such tensor unit towers. So if you carefully plan the scheme, you can do that. So you can reduce the use of heavy construction machines and by replacing the effort of human or labor power at a construction site. Okay. So thank you for your kind attention.
I would like to thank very much Professor Kawaguchi for his very inspiring and interesting lecture. I would like to say hello, by the way, to Professor Zingoni. It is very nice to be at the same time in Japan, Poland, and South Africa. And right now, due to our time limitations, unfortunately, we need to skip discussion to maybe coffee break or later breaks. And I would like to introduce the next lecture. This lecture would be delivered by Professor Błazik-Borowa from Lublin University of Technology. The title of this lecture is Finite Element Method Scaffoldings Modeling Based on Laboratory Test. Just a few words about Professor Błazik-Borowa. She works at the Faculty of Civil Engineering and Architecture, Lublin University of Technology. Currently, she is the head of the Department of Structural Mechanics, so the same as ours. Her teaching and research activities are related to structural mechanics and computer methods. She deals with the research and simulations of environmental loads, as well as research and numerical modeling of engineering structures, in particular scaffoldings. She created a scientific school at the Lublin University of Technology, in which scaffolding and construction formwork are the mainstream of scientific interest. She's the author or co-author of 211 publications, over 180 technical studies concerning construction designs, technical designs of scaffoldings and formworks, as well as expert opinions. She is active in scientific associations, is a member of expert advisory institutions, and was a member of 27 conference scientific committees. Please welcome for your lecture here.
Thank you for your introduction. I hope we will see my presentation. Thank you also for inviting me. It's a great honor for me to present my research in this symposium. I think that in this moment, my presentation, 2 minutes. Okay. I'm afraid that it isn't a presentation. It isn't proper presentation. It is also from Łódź, but it was 2 years ago. Yes, but PowerPoint, please. Okay. I would like to present modeling of scaffolding. Yes, okay. Based on laboratory test. The main subject is the presentation of calibration and verification of numerical model, but I also will show the comparison of two approaches to the analysis of computer simulation results in scientific research and engineering practice. This figure shows the scaffolding around Scheibler's chapel in Łódź. Scaffolding are assembled from components with different level of geometric complexity, stand, ledger, brace, are slender and can be modeled with use of frame elements, but platforms which includes a few deck and joints have a complex geometries, and I will pay the most attention for this object because the introduction of scaffolding system to market have to proceed by many laboratory tests. The procedure of this tests, laboratory tests, includes the following stages: laboratory test of material properties, laboratory test of individual components, laboratory test the scaffolding, but it is the special configuration scaffolding, and with this test is called a global test. And on the basis of this laboratory test, we prepare a numerical model of scaffolding. The stand ledger connection is subjected to internal forces, and the most important for a numerical model are bending moments which act in two planes, vertical and horizontal. And these figures show the laboratory test for these internal forces. The results of this test are stiffness as a function relationship between moments and angles, and load bearing capacity at bending for moment along a vertical and horizontal axis. The stiffness of stand ledger joints is taken into account by introducing a transition element. It is elements with length, constant length. I assumed 5 centimeters, and with cross section, rectangular cross section. In order to calculate the properties of this element, we use results from test. These results from test are shown here. The first, we calculate moments of inertia. Next, from these formulas, we calculate the dimension of rectangular cross section. And next, we calculate yield strength. The final result are shown here. The joints, model of joints is simpler than a model of scaffolding platform. And the geometry of scaffolding platforms are very complexity. It is one deck. The scaffolding platforms play a double role. They serve as working platform, and they ensure the horizontal stiffness of a scaffolding. And if I will say the model of platform, I will understand the model of horizontal stiffness of the scaffolding, which create by the platform. The platform model is to ensure an equivalent horizontal stiffness determined in laboratory test, and the platform is modeled by 4 truss elements, 2 elements along decks, and they are called longitudinal elements, and 2 elements which are crossed, and they are called crossing elements. In order to calculate or evaluate of properties of these elements, you have to use the results from measurements, and we have 2 types of laboratory test. The small configuration of scaffolding with platform is loaded with a force perpendicular to platform and in a parallel direction to platform. I show static scheme, because I think that this photo are not clear. The results of both measurements are the force displacement relationships, which are shown here. We assumed that cross-section area of these truss elements are constants, and we assumed this value. Elements have the same material properties in compression and tension. The influence of longitudinal elements on the stiffness at perpendicular loading is negligibly small, and each graph, each fragment of sigma epsilon graph, which will present properties of our elements, is determined on the basis of suitable part of force displacement. Because of time is short, I show only one example, one small part of this derivation of this formula. This part of sigma epsilon curve for crossing elements is evaluated on the basis of this part of the graph force displacement. All increment of epsilon of strain are calculated as quotient increment of length of elements and the input length of these elements. The increment of stress is calculated as the difference, as quotient, the difference between internal forces and cross-section of 4 elements. Internal forces are calculated on the basis of the sum of projections of force in the y direction. For crossing elements, for parallel elements, we use the sum of projection of force in the x direction. This formula is inserted here, and we obtained increment of the stress. Of course, the quotient of quotient stress and strain allow us to calculate the stiffness modulus, plastic modulus. The numerical model of platform must be corrected due to the future of the laboratory test. For example, we have clearance in wheel guides. And after this correction, after a few iterations, we obtained final result to curve sigma epsilon curve for crossing elements and for longitudinal elements. And this figures show the comparison calculation results and measurements. There are 3 types of results, 2 types for measurements, because this line shows the results, the average values measurements results. This line, there are 2 lines, but they coincide. These 2 lines represent measurements results determined in accordance with standard. It means that our values, results of measurements are defined as 5% quantile and calculation results. The last test, it is a global test. This figure shows the scheme of scaffolding during laboratory test and the location of the point of measurement of displacement. We have 12 points and 12 functions which were measured during laboratory test. During this test, the scaffolding is subjected by horizontal force and by vertical forces, and vertical forces increase until the scaffolding loses its load bearing capacity. This laboratory test were made that we obtained results which we want to use to calibration of numerical model. And model of scaffolding is shown here. The calculation were made with Autodesk simulation multiphysics program. Non-linear static analysis were used. The forces were applied in subsequent calculation steps to map the forcing in the global test, and this figure shows our forces. And the results, the laboratory, the global test and calculation results. The main of the results are displacement in 12 points as function of the forces. Forces or force, because we have the same vertical force which are applied here. Scaffoldings achieved the following shapes. It lost bearing capacity. Both figures show similar bend of stand in the middle vertical. And the load bearing capacity from calculation is 10% smaller than critical value from laboratory test. And the final comparison results of calculation and measurements. We have one type of measurements and two types of calculation. First variant is obtained for the value defined as the 5% quantile for confidence level at 75%, and second variant of calculation is obtained for properties which were calculated on the basis of average values from measurements. The first variant is used in engineering practice, and results of calculation have to guarantee the safety of the structure. Therefore, model verification criteria is to obtain a smaller displacement at the same loads. The graph from calculation have to be below the results from measurements. And critical force should be smaller in calculation than measurement. In scientific research, the model verification criteria means the most faithful and accurate description of the behavior of tested object. And for engineering practice, the verification criteria are met and the model can be used to assess complete scaffold. For scientific research, results obtained for average value from measurement are better, but it is not possible to accurately reproduce the measurement results because each joint has a different stiffness. Assembling decks in ledger allows for different arrangement of the handles in relation to the profile. And I know that we haven't time. So conclusion, in the paper there is shown an engineering approach to the verification of calculation results. As it can be seen, the calculation results are similar to the results of laboratory tests and they meet verification criteria for engineering practice. Obtaining full compliance of calculation and laboratory tests is not possible because the scaffolding contains too many components and joints which may differ significantly from each other. For scientific research, the computer simulation of a global test cannot be released on a deterministic approach. Model parameters should be generated as a random process, and it is the task for us in future. Thank you for your attention, and I'm sorry for my pronunciation.
Thank you very much for the very interesting lecture. It was very nice to see the third conclusion. We are interested a lot in random processes and stochastic analysis here at Łódź University of Technology, so we can cooperate in some way. I would like to introduce the regular lecture from Czech Republic. This is by Nela Freiherrova, Marie Hornakova, David Juracka, and Marek Kawulok. This would be dependence of membrane structure deformation on different material. We have 15 minutes for your lecture. Hello.
Hello, thank you for your introduction, our contribution. So let's start now. So Yeah, I will start the presentation. So, hello again to everyone. My name is Nela Freiherrova, and I am PhD student at the Department of the Structural Mechanics at the Technical University of Ostrava. And together with my colleagues, we prepared a contribution called Dependence of Membrane Structure Deformation on Different Material. So, our interest in membrane and lightweight structure leads to design of the small membrane structure for roofing this experimental equipment, which can be seen on figure 1. It's located in the campus of our department, and it has been designed for static load tests and for other experiments for the investigation of stress and strain relations for soil structure interaction. Currently, it's not protected against the unwanted weather condition, so together with the dean of our faculty, we agreed to try to design and roof it by small membrane structure. This project is solved in a student grant competition, which is called Experimental Verification of Form Finding Process and Cutting Pattern Process of Membrane Structure. And another area in the field of membrane structure is our team project, the doctoral grant competition, which is interested in analysis of behavior of membrane textile materials. So, here we can see the initial visualization of our design. We decided to design the membrane structure in a shape of hyperbolic paraboloid and use the existing foundation of the equipment as a support system for the column. Also, we tried to keep the range of the columns from 0 till 15 degrees. For numerical analysis, the software RFM was chosen. The RFM software has special add-on module, RF form finding, which is very useful for design and optimizing analysis of membrane structures. We can see here the use of existing foundation for pin-supported columns. And there are also 2 rods for every column and inserted cables along the entire fabric for pre-stressing the textile material. The initial pre-stress was set as 1 kilonewton per square meter in both directions. And on the right picture, we can see the final model after form finding calculation, which is then used for loading the whole structure. So when we were solving the choice of the material, we chose the polyester based textile material with PVC coating. Also from the reason that we are trying to perform uniaxial and modified biaxial tests on this type of material. These types are divided into 5 categories depending on their properties, and we took over the literature first for classes and their characteristics and did analysis which type will be the most suitable for our design with respect to the pre-required deformation limit. As a material model in RFM software, the 2D orthotropic elastic was chosen because it's the closest type to use in the design of membrane structure. However, for design the materials in this software, it has to be known the values of elastic moduli and Poisson's ratio, And by the way, that's we are trying to, and we are interested in testing and evaluating these characteristics from biaxial test, because data sheets of the materials mostly shows only the tensile strength values. In the table 1, we can see the properties and characteristics we used for analysis. Here we can see the load by snow. We choose this load case because for analysis, because it is quite simple to implement and apply in numerical models, and also because in winter time it can be critical and also long lasting. So the value of the snow load was determined according to Eurocode and current location, which is Ostrava, and it was set as 0.8 kilonewton per square meters. On the figure 7, we can see the final global deformation for one type of analyzed types after the loading the structure. So for membrane structure, we all know that the deformation or big deformation are nothing bad. However, in this design, we were limited in the sense of deformation because of experimental equipment is under the designed structure. So for evaluating the results, we have a limit of a maximal deformation, and it was determined as 200 millimeters. This limit should ensure that the membrane structure and the experimental equipment will not collide together. So as can be seen, to this criterion is the most suitable the type 2 of polyester-based material, which were then chosen for the structure and for continuing our work. So let me tell you something about the current state of our project. So now we are trying to solve the wind load case. This part is the field of interest of my colleague, PhD student, Mr. Kawulok. For the wind load cases, the CFD simulation software AirWind was chosen. It's a steady state solver for incompressible turbulent flow. And the results of the solutions is a pressure field on the building envelope and the three-dimensional wind speed field. A total of 8 flow directions, which can be seen on the picture, are considered for analysis. It's because the amount of the directions is given mainly by the asymmetry of the structure, so it's necessary to consider all possibilities. At present time, a time-consuming calculation is performed. It also takes into account the surrounding of the structure overall, and after the calculation is finished, a study of turbulent model with different turbulent intensity settings for all 8 directions will be performed also. Here we can see the example of the results for one chosen direction with a K epsilon turbulence model and turbulence intensity of 1%. And we can see the upper phase, lower phase, and in direction of wind flow results of CP coefficient for winter. So let me tell you some conclusion. So the numerical analysis was performed to determine what type of material should be chosen in terms of deformation for our design of membrane structure, and the analysis was did for snow loading case. Our evaluation criterion was given by handling space between the structure and the experimental equipment, and it was set as 200 millimeters. And for this criterion, the type 2 of polyester-based material was chosen as best option. And our continuing research for modeling in RFM, as I told you before, elastic moduli and Poisson's ratio obtained from biaxial tests are needed. However, it's not easy to get closer to these characteristics, and that's why we are solving it in our other project, which is focused on this, evaluating these methods. So maybe in the next year on this conference, we can tell you something more about this topic again. This is all from me. Thank you for your attention and for possibility to tell you something about our research.
Dear Nela, thank you very much for your presentation. We've seen everything. Unfortunately, due to time limitations, we are unable to deliver any discussion. However, I would like to say personally that interfacing of computational fluid dynamics with structural analysis was very interesting, and we invite you to visit Poland next year. Thank you very much.
Thank you very much.
The next lecture would be delivered by Karl Winkelmann and Jan Sikora from Gdańsk University of Technology, and the title would be Simulation-Based Sensitivity and Assessment of a Truss Lookout Tower to Corrosion-Induced Degradation. Please start.
Thank you very much, Honorable Chairman, dear guests. 1 minute, okay. So I will take my time, and I will thank cordially for the invitation for the organizer for their hard work. It's so nice to be here in Łódź in person during the pandemic ages. Okay, as it was priorly introduced, I'm Karol Winkelmann. I'm from Gdańsk University of Technology, and together with Ms. Sikora, we are currently running a study on the simulation-based sensitivity assessment of a lookout tower to the degradation induced by corrosion. The main aim of the study stands for itself. We are aiming to present the sensitivity analysis, but with the most simple methods that can be applied so that the approach can be useful to engineers in design offices. And also the corrosion, we expect that the corrosion can be represented by deteriorating, diminishing the Young's modulus and the yield strength of the material that the tower is made from. The scope of the study, you can see below. We assemble a model, we take a full ULS and SLS analysis of the model, then we determine and define the random variables of the problem to express the corrosion processes. Then we make simple element-wise sensitivity analysis. Further, we take more advanced steps, but relatively simple techniques. And at last, we use the response surface method. The tower is a real-life object. It's located in Kozacza Góra in Gdańsk, Poland. What is interesting, the tower is located in a dense mixed forest, and that's good for the tower because the tower tends to vibrate, and the vibrations are reduced by the presence of the trees around, so the wind doesn't take such harsh actions against the tower as it could be if the tower was on open air, for example. You can see the parameters of the tower. I won't be reading them all, but what is interesting, that the elements of the tower are generally made from the same profiles in the entire geometry of the tower, because there are some towers where the geometry of the column profile changes upon the height of the column. This is not in the case. All used profiles are the same throughout the tower, so it's easy to group them and to transfer them into parameters that we investigate. The FA model, finite element model, was assembled in RFM by Global. As you can see in the picture, really everything can be divided into simple groups where the crossbar, the columns, the transoms have all the same cross sections and can be easily grouped and easily defined as one simple object that is hit by corrosion. As for the loads, standard loads were taken. For the live load, also a simple dynamic load was introduced, and the combinations ULS and SLS based combination standard for the design offices. The tower is made of S275 steel, so it's a standard steel for constructing such objects. As you can see from the simple preliminary analysis, we determined that the stresses are relatively low. As you can see, the maximum value of the maximum value of the stress introduced to the element in relation to the limit stress is 0.83. So the tower is safe. It's made safely according to stresses and according to displacement, but vertical displacement. That is very important. They are lower than the limit set by the Eurocode. But what should be said here, the tower is endangered by the accelerations of the deck. But this is not the case of the study. But indeed, if you go to the top of the tower and you take one step, you can feel the vibration, the acceleration that is induced into the deck. So we don't believe that this was analyzed in the original problem, original design of the tower. Corrosion. Now we want to implement corrosion, and we take, according to the formulations found in Guo and found in the works of Juricic and Parunov, that the elastic modulus and elastic limit, the change in those parameters, can express corrosion nicely, corrosion processes. And here you have a graph taken from the work by Guo, clearly shows that for different types, different strengths of corrosion, the modification, the deterioration of those values of those material parameters really occurs. We have assumed that both the volumes go down from 100%, that's the initial ideal stage, to 80%, and the 80%, according to the formulas that can be found in Guo, are equivalent to circa 60 years of constant usage of the tower, constant corrosion, without any repairs done in the meantime. The elements of the tower, as you can see, there are 7 different types, 7 different groups of elements, and they were considered as parameters investigated. We have, in the beginning, we have done a simple simulation analysis where we took only some standard points, standard models. We have created 35 models, 5 for each parameter, 5 for each type of cross-section. When we consider 100% the initial state, and then the corrosion that's reduced those parameters, yield, stress, and Young's modulus to 95, 90, 85, and 80%. Thus, we can see a simple sensitivity assessment where you can find that the groups, that the staircase, the main elements of the staircase, and the main transverse bracings are the most sensitive, that corroding them is the most dangerous action that can be done to the structure in time. Now we have turned to more sophisticated techniques, if I can say that, because we still based on the simulation, that the recalculation of FA models of the tower. First, we have applied the one-at-a-time techniques that defines the density as the quantification, the description of a result that one single variable has on the remaining ones. So we set the P1, we say that the staircase, the metal of the staircase is ideal. That means constants. And we say that all other elements degrade, and one at a time technique expressed that the sensitivity is the biggest when, without changing the parameter in question, the change in all parameters display a scatter cloud, which is relatively scattered with a big scatter. And as you can see in the picture, these results generally suggest and describes mathematically what we have seen here. It generally defines the same results as the preliminary analysis, but here 700 models, 100 models per each variable are used, and for the combination, again, 100 new models are defined. So it's very time consuming, but here we have numbers, and the numbers can be turned into sensitivity and indices, and the sensitivity indices can be used in further calculations of reliability or something related to failure. Also, a histogram approach is possible using the same models that were applied previously. Here we force a histogram, we present a histogram defining the x-axis as the material effort of the element and defining the number of the samples with the observed effect. And as you can see, if the tangent line to the histogram goes upper, is the slope of the line is higher, then the sensitivity is bigger. And also with the numbers, we can calculate the sensitivity indices, which can lead to further remarks. Also, we have applied a direct Monte Carlo approach, but not to define sensitivity indices, because as it appears, considering 100 samples where all the variables turn at once, where there is no variable hold in its ideal state, ideal condition, considering 100 samples is not enough, and those results that we get from the scatter clouds approach are clearly not good, are clearly erroneous. But we have done this simulation to point out that many of the samples, many of the towers which have been degraded in the numerical model lead to failure, lead to structural failure. So we are clearly sure that in some time after using the structure, when it's not so late, not 60 years, but we are now calculating how many years would it take for the structural failure to occur. But as you can see, that is a large problem. So again, corrosion in Gdańsk or near the seaside, the corrosion is a major problem. Also, I have used the response surface method to assess the sensitivity and indices. And as you can see, using a prior analysis where we can define those two groups with the major influence on the tower itself, we can form a dependence. We can investigate the impact of the correlation that is imposed by those two crucial groups, degraded groups of parameters to the entire response. And as you can see, with only 25 points are added, 25 FA models are considered, and we have a full image of the correlation that occurs when the corrosion hits the two main groups of elements, those two groups with the initial highest level of stresses in them. And sorry for the little typo, because the sensitivity of the variable number 2 is lower. It's 164. Sorry for that typo. So also we can see that evaluating the sensitivity with such simple techniques with using little models is possible. To conclude the paper, as we can see, there is a possibility to implement simplified sensitivity analysis procedure when we can recalculate FA models. Well, it's a good tool for modern day engineering because the computer power goes up constantly. So recalculating the models are now a question of minutes and not days or weeks. However, we must know that the appropriate sample number must be generated for the convergent analysis should be performed in order to ensure that the results are trustworthy. And as you can see, the failure of the tower near the end of the operation time is very possible. So repairs should be planned, should be taken, and we are planning in our study to indicate upon how many years they should be introduced for the tower to stay safe. And this sums up future plans, which are based upon those things that I have mentioned, and also the assessment of structural reliability. Thank you for your kind attention.
Thank you very much for your interesting lecture, very close to our interest. I'm terribly sorry for wrong introduction, not John Sikora, but Joanna Sikora, but you know. Okay, thank you very much. Right now we have a coffee break, but just before the coffee break, to make a discussion very hot, from yesterday, our Ministry of Education and Science changed a list of the journals. So the points are different. We start optimization once more and preparation of all the documents necessary for evaluation. Thank you very much.